Okay, now what we have on the screen is the basic parent graph of a rational function. So make that solid. So if you have f of x is equal to 1 over x, this is that general sketch. Notice you have a horizontal asymptote on the x-axis and a vertical asymptote on the y-axis. And I'll explain a little bit about why that is. Well, the vertical asymptote is easy. If we put 0 in for x, you can't divide by 0. And when there's a 0 in the denominator, at that x value, it forms a vertical asymptote. Okay, so there's that. Well, now we have a bunch of stuff going on. First of all, it's a negative function, which means this graph, instead of being in this quadrant, if nothing else was changed, just the negative sign, this graph would look like this and this. So we know now that the new graph, the graph that's right here, will be in that quadrant. And I'm going to erase this other stuff. You saw what the basic parent graph. We now know that it's going to be in this quadrant. And we're going to use all of this transformation. So normally that point right there and that point right there would be used. But because it's a negative graph, normally that point would be there and that point would be there. But now we're going to look at transformations. First of all, we want to look at this vertical asymptote. Normally, if it is 1 over x, when x is 0, just like this, x is 0, there's a vertical asymptote. So normally it would be where x is equal to 0, you have a vertical asymptote. But if we look at this function, well, what would zero out positive 1? What zeroes out positive 1? Negative 1. So where x is negative 1, so everything has to be shifted left. So this point will be shifted left 1. This will be, the vertical asymptote will be shifted left 1. And that starting point would be shifted left 1. All right, so we have the left and right shifted. Now we also have a horizontal asymptote that's at y is equal to 0. This is a little bit tricky. The reason that we have a horizontal asymptote where y is equal to 0 is because when the x in the numerator is smaller than the x in the denominator, whenever that's the case, oops, this exponent is higher, that's x to the 0, x to the first. Well, that's what we have here. 1 means there's an invisible x to the 0 over x. That's x when it's smaller in the numerator than in the denominator. The horizontal asymptote will be where y is equal to 0. However, this tells us to move everything down 2. So not only will this horizontal asymptote be moved down 2, so now instead of 0, we're going to be down there at negative 2. But these points, these starting points, will also move down. So I'm going to shift all of that stuff down. 1, 2. Okay, so those will be our starting points right there. I'm going to go ahead and erase this because I can get rid of that and say where y is equal to negative 2, because right there that tells us we'll be down there at negative 2. So where the vertical asymptote is, that will be undefined. And by the way, if we have to identify domain and range, domain, you're going to use this point. We're going to be coming from negative infinity. We're going to get really, really close to 0, and then we're going to turn. And then on this side, we're going to be really close to 0, and we're going to turn. So the domain for this will be, oh, I'm sorry, not 0. We're there at -1. And normally you would be at 0 when the asymptote's at 0. But the asymptote's now at -1. So for the domain, you just use the asymptote value to plug into the domain. All right, so let me erase this stuff. You don't need that cluttering that up. And I'll put back those starting points, one away from each asymptote, just like that. All right, so that's our vertical asymptote, our domain. And for our range, erase all this stuff. Well, our horizontal asymptote would normally be at 0, and normally we would be going from -infinity all the way up to 0 and then turning. And over here we'd be really, really close to 0 and then we would turn. Well, this graph is negative, but even though it's negative, so we're going to be over here going from -infinity all the way up to -2 and then turning, and then really close to -2 and then turning and headed off towards positive infinity. So its domain and range is going to look really, really similar. So the range, we're going to use that value, will be -infinity getting really close to -2 and then really close to -2 and headed off to positive infinity in the up and down, and domain is left and right. So we've taken care of this, we've taken care of this. We know it's going to be negative, and negative means it will be over here and over here. So we took care of that. Erase all that stuff. The only thing we have left is, what does this tell us? Well, that's just like if we said 4 times that function. And so remember, 4 means vertical stretch, or 4 times as steep. So normally we would touch here. Well, 4 times that, normally we'd be 1 away. We're now going to be 4 away vertically because it's a vertical. Whoops, I did not mean to do that. So instead of at 1, we're going to be up 1. Oh, doggone it. 1, 2, 3, 4. And then this one right here, hopefully I can move it without. That's 1 away down. We're going to go 1, 2, 3, 4. And then when we draw the graph, oops. When we draw the graph, you just need to remember that we're still really close to the asymptote, but then it's stretched. So it's not going to make that elbow turn. It rises more steeply, more quickly. So we're going to be doing this. And this is how you graph rational equations using the transformation pieces. And you can still plug in x values there. It's just that you don't have to. And typically we're going to want domain and range. All right, that's it for now.